Hey, I realize now that 1.7 introduces the rate law from um, looking at the different reaction steps. And what they do is stupid in that they introduce something called equilibrium. But equilibrium isn't introduced till the next chapter, chapter 2. So it's stupid of them to introduce it without explaining it to you. When you mix two substances and they react, it looks like this graph over here. And I'll try to enlarge it because it's important. The substances are at a certain concentration, let's say 2 moles per liter. Let's just ignore that it says moles there, moles per liter. And as they react, their concentrations go down. And what happens is they create a product that starts at 0 because there was nothing there before these two items were mixed together. And as the product is created, it increases in concentration. So the reactants decrease and the products increase. And there's this balance. There's nothing lost or gained in the system. There's a balance. Now notice that they both flatline after a while. Also notice that when they do flatline, there's still a concentration of the reactants and there's a maximum concentration of the products. We'll forget what influences these, things like temperature, pressure, etc. for now. I want to make a point. My point is there's still some reactants unreacted, and there's still a product that could be reacted from those reactants. This is a state of equilibrium when it flatlines like this. It's done reacting. It's done all it can. You can influence it and make it react more, and that's what chapter 2 is about. But in chapter 1, they introduce equilibrium, and here's the formula for equilibrium. The equilibrium constant, called I think it's just EQ, or it's KEQ, KEQ, is equal to the concentration of the products, and it doesn't matter how many products there are, you can have multiple products, divided by the concentration of the reactants. And again, it doesn't matter how many reactants you have. Keep doing like that. But one thing you learn is that you don't include reactants that are liquid because they're not really influenced or affected by equilibrium. So if there was water, for instance, on one side of it, you don't include that in your KEQ. And you include things like gas. And you include aqueous. So a better way to say it is you only include aqueous and gas in the product reactant table. So that means in this case, because now I'm going to make a copy of this formula. There's one other key to it. In this case, the product is HF, not 2HF. You always just focus on the compound, HF. There's no other product that can have concentration. There's no other product, so we just skip it. But there's one key important point. Because it has a 2 in front of it, I'm going to just make a copy of this and go back. You have to put the 2 as an exponent. So you put their coefficients as exponents. Notice that H2 gas doesn't have an exponent, doesn't have a coefficient. So there's going to be no exponent to it. And this also doesn't have a coefficient. So there's going to be no exponent to it. And this is the equilibrium constant statement. You come up with it, KEQ, from any substance, it will reach a balance. And what you learn in time is, obviously, if this came out as 5, let's just pretend this came out as 5, and this all came out as 1. 5 divided by 1, it clearly comes out as 5. But it's obvious from the 5 that there's more products than there are reactants. So the equilibrium would tell me, from KQ of 5, that this reactant has mostly favored the product side. If, however, I only end up with, let's say, one concentration, one molarity of concentration to 5 reactants, this comes out to 0.2, 1 divided by 5. This tells me this is less than 1. This tells me this reaction left most of the reactants on the table over here. And you look at it as a seesaw. Now, what we get into later is that you can affect the seesaw and create more products, and you can affect the seesaw on this side and create more reactants. And that's the whole point of chemistry, is we're learning to manipulate things that happen in nature. But the equilibrium statement is what I want to teach you. KEQ is equal to the concentration of the products only for gas and aqueous products, divided by the reactants, and you put an exponent based on their molarity. This is what we use in 1.7 as one of the steps to come up with a formula to come up with the ultimate rate law step. They kind of gloss over that in 1.7. They assume you know KEQ, but that's introduced in chapter 2. So my mistake for implying that you should already know it, this is introduced in the next chapter.